Let me record again. Okay, so I was saying that with the figure we have, that's figure 7.2, okay, which is basically Darlington pair arrangement of transistors. And I was saying that transistor arrangement in Darlington pair is nothing but connecting two transistors in series, okay? You have two purposes when you get this done. That is, one, you increase the current, okay, like you can see the figure, okay? I hope you can see my cursor moving. Yeah, so you can see in the figure, D, like we have two transistors, one label as D for dog, and then one label as M for money, okay? So D and M are two transistors, but if you observe carefully, you realize that the emitter of transistor D is serving as base to transistor M. Hope you can see that. Okay, good. So that is what is happening, all right? And then you lump the collectors together. So they are basically at a common, sorry, not at a common potential. So the base of transistor D, okay, is also looked to diode 1, D1. Okay, D1 is a diode. So diode 1, we have two diodes there. Diode 1 and then diode 2. Okay. So that in turn is also connected to the base of transistor M. Okay. Now with these arrangements, we are trying to achieve two things, or mainly in this case, one thing. For the current gain, okay, you need a current gain, all right, to be able to enhance your switching abilities. Okay, so the overall current gain in the Darlington circuit, okay, is giving us beta is equal to beta for transistor M, and then beta for transistor D. That is the product, plus beta M plus beta D. Okay, so that in effect, you realize that this times this plus this actually improves the overall gain. Okay, so the discrete diode as D1 helps in speeding up the turn-off time, okay, of the main transistor, whilst D2, okay, is added for half and then full bridge amplification. So that is the concept of this construction, bringing in Darlington pair. Okay, we said previously that we need Darlington pair. Okay, though we are talking about power BJT. The characteristic curve, okay, is a bit different from the characteristic curve for, if you like, that of ordinary BJT. Okay, so as we have in this figure, okay, figure 6.8, this is the characteristic curve, if you like, the collector current with respect to collector emitter voltage, okay, the curve, right, which is basically the characteristic curve described in common emitter configuration with reference to, this is, or maybe I should ask you, is this input or output characteristic curve of BJT, what we are seeing in figure 6.8?
It's an output characteristic curve.
Is it an input or output characteristic curve?
The output
An output characteristic curve.
So, obviously, an output characteristic curve. Okay. Yeah. So, if you look at this, and what I have just shown you, okay, previously, right? That is this curve. You realize some bit of difference in the two, okay? Yeah. So I'm admitting some people in the waiting room. They are joining us. Okay, good. So let's briefly talk about this. So this is the voltage current characteristic curve of a power BJT. Okay. So you can see the collector current versus collector emitter voltage, basically. But there are some other elements that are on board to make sure we have a different curve compared to the ordinary BJT. Okay, so the figure depicts that. Now, the characteristics of Darlington pair are quite similar to same as we have here. So briefly, let's just describe this. But as you can see, we have the collector current IC on the vertical axis, and then collector emitter voltage VCE on the horizontal axis. Okay. Then we have what we call hard saturation region, and then quasi-saturation region, and then also we have the active region. Okay, so basically we establish three regions. Okay, the high saturation, the quasi-saturation, and then the active region. Okay, and you also have some level of breakdown. So let's quickly describe this in the next slide. So there are four regions. Okay, so you have the cutoff, and then of course your cutoff region, okay, is basically your region where your base current IB is virtually zero. Okay, this particular region. Okay, so you can talk about four different regions, so that when you look at this for the signal BJT, you have three regions. That is the cutoff, like you can see here, and then the saturation region, and then the active regions. Okay, in the figure here. So when you also look at that of the power BJT, you will have the cutoff region which will exist here, and then you also have the hard saturation region, and then the quasi-saturation region. So it simply means that for the power BJT, we have two layers of the saturation region, what we call the hard, and then the quasi-saturation region. Then also you have the active region, which is making it four. So in describing it, your cutoff region, okay, your base current is basically zero. Okay, in the cutoff region, the base current is virtually zero. Okay, so you have negligible, if you like, current flowing at the base. Okay, because of that, no collector current will flow, and then your transistor is considered to be in the off states. Okay, so that's what happens in the cutoff region. Okay, I hope you are with me.
Yes, sir, we are with you.
Are we together?
Yes, sir, we are together. We are together. We are together, sir.
From one person.
Yeah,
So, Blessing, you can hear me?
Yes, sir.
Okay. All right. So, let's continue. Now, so that's the concept of the cutoff, okay? Now, in the quasi-saturation region, okay, and that of the hard saturation region, okay, the base drive is applied and transistor is said to be on. Hence, collector current flows depending upon the load, okay? All right. So, a base drive circuit is nothing but I think, or maybe I haven't talked about it, but a circuit that will help you to actually turn on a transistor, okay? That is what we call a base drive circuit, okay? So, yeah, so that is what is helping you mostly for the device to actually come on. Okay, so your base drive circuit. Okay, so I have it on the slide for you. Okay, you require that to supply the base currents. Okay, to switch on the device or switch it off. Okay, as well by diverting the base current. You know, like we said earlier, once your base current IB is equal to 0, okay, no collector current will flow. All right, because of that, you're going to have the transistor in the off state. Is that right?
Yes, sir.
Very good. So, if you have a base drive circuit, it would help you to aid certain amount of base current to flow for the device to conduct, and at another point in time, you will reduce the base current with the help of the base drive circuit, and the device can go off because no collector current is going to flow then. Okay, so that is what it is. This slide, we will come to it, but that is just to have an idea about a base drive circuit. Yeah, so coming back to this, with the quasi region and then the hard saturation region, you apply the base drive, okay, to the base circuit, and then your transistor will be on. Will cause some current to flow in the collector phase side, depending on the load, of course. So the power BJT is never operated in the active region. Okay, the reason is we are not interested in this for an amplifier, but we want to use it as a switch. So we just want to make sure we move between cutoff and then saturation. That will cause the device to switch off and then what? On. Like I said earlier, for our power electronic devices, in most cases, or practically, we are using them as switches, off, on, off, on. Okay, so when we are using that switching behavior to control a process, okay, so these power devices that we are talking about, power electronic devices that we are talking about, we are more interested in them as a switch. And for a transistor, we are not going to use it as an amplifier, but we are using it as a switch, okay? All right. So our device here will be operated between cutoff and then saturation, okay? Now, the BV source, okay, or BV source is the maximum collector to emitter voltage that can be sustained when the power BJT is carrying substantial collector current. That's the BV source. When you look at the curve, see, this is that's axis or the region, if you like. So the BV source. So that is basically to have an idea of the amount of collector current, okay, to emitter voltage that we can handle or we can sustain when certain amount of collector current is flowing, okay. It is actually a voltage. So that's why we have BV, sustain, okay. So we are helping to sustain certain amount of current, collector current, with regard to collector to emitter voltage. Okay, so that is what it is when we are talking about this. Okay. All right. Also, we have BVCEO and then BVCBO. Okay, collector to emitter. This is collector to base. Okay, so if we who is now coming? Wow. Now, so your BVCO, that is also the maximum collector to emitter breakdown voltage that can be sustained. Okay, so the sustenance of it, that's why we are introducing the cells and so on and so forth. So that can be sustained when base current is 0. Okay, and the BVCBO is also the collector base breakdown voltage when the emitter is open circuited. Okay. So these are some other parameters that are introduced in the Power BJT to make it different. Remember, we are so much concerned about the breakdown voltage to make sure that we don't allow undue voltage in the reverse to destroy the PN junction, so that if the device goes off and is supposed to come on, it will not be able to, or suppose it stays on and then it's supposed to go off, it will not be able to go off because you have damaged the depletion layer. Okay, within the layer, the PN junction, the depletion layer, if you allow for recombination, you remember we talked about reverse recovery time, TRR. You remember?
Yes, sir. Yes, sir.
Okay. So there's a need for recombination to take place, and then the device can switch again from the off to on state, off to on state, and so on and so forth. Okay, so that is what is happening. All right. Now, the primary breakdown is because the one who just came on, you can mute your microphone again. Okay. The primary breakdown is because of avalanche breakdown of collector base junction. Okay, so large power distribution is normally normally leads to primary breakdown. Okay, so you can also have the concept of primary breakdown, which is as a result of avalanche breakdown. Okay, so when that happens, basically you're going to have an issue. Okay, so that is the primary breakdown here. Okay, so you have the primary and then the secondary, and these are as a result of the avalanche effect. So if we are not able to block a reverse voltage and it comes up, it would promote this breakdown. So okay, or promote them. Okay, now we can quickly look at the switching characteristics of Power BJT. Okay, but like I said earlier, we want to use it as a switch. So let's look at its switching behavior. Now, so your BJT cannot be switched on and off instantaneously. Okay.
But you said cannot be switched on and off.
On and then off instantaneously. You understand?
Okay. Okay.
So they're on this slide. Finite off and okay and off time is required, right? So there should be some time span for your off on, like we've seen some time back in reverse recovery. Okay, there should be some switching time. Cannot just happen. Once you see on, then the thing is on. And a typical switch, you would appreciate, because of the human eye, you will appreciate that when you press the on switch, the thing actually started immediately. And it came back from off to on and so on. The reason being your time, when we even say something happened within 5 microseconds, your eye will not be able to handle that. Our natural eye is not able to handle that time. Maybe we can appreciate 1 second, so that if the time lapse is just 1 second between a switching process, that one you may be able to appreciate it. But if we are going to switch in the micros and then in the nanos, it is very, very fast. But for your switches or our power electronics circuitry, it is, or there's that time delay, okay? Time delay for the thing to actually move from off to on. Okay, so we can talk about maybe a switching time of 10 microseconds, maybe 50 microseconds, and so on. It happens very fast, but with our natural eye or naked eye, we are unable to appreciate this switching process. So that's what we are saying. It doesn't happen instantaneously. Okay. Now, most losses in Power BGT occur during its switching process. You guys, you are sure we haven't talked about these things? Anyway. You are sure?
Yes, sir. Yes, sir. Yeah, sure. Yeah, sure.
All right. So, power losses, okay, when you are doing switching. So, the longer it takes for the thing to switch from off to on, it means you are incurring a lot of losses. Okay. Once it is taking time for the thing to move from off to on, and then back from on to off, and so on and so forth, your losses will increase in the process. So it will be to your advantage to design a system that will switch very fast. If it does so, then you would have dealt with switching losses. Okay. All right. So let's look at the curve a little bit. So figure 7.4 is the dynamic switching characteristics, okay, of Power BGT. So in this case, we are just looking at resistive load. Not an inductive load. Okay, so like you can see, this curve is basically giving us an idea of some time period or some processes. Okay, so you have your base current, collector current, okay, collector to emitter voltage, and then you can talk about TD, TRI, okay, then T on, And then you also have T off. T off has two main components, that is TS and then TFI. Okay, so also when you take T on, you have two components, TD and then TRI. Okay, then we can look at some percentages of some happenings in this process. So let's quickly look at that. So in practice, the rise and fall of currents and voltage is non-linear, although linearly depicted as we have in this whole thing. Okay. I think in the next 10 minutes, we should be closing because the software or the app is reminding me that I am running out of time. I have 10 minutes more. Okay, so
Yeah.
to
And it will be 10:32. Yes, sir.
run it up this way. Okay. Yeah, so let's look at this one. So T on is the switch on time, which is broken into a TD and then TR, like I said earlier. So the TD is the time required to discharge the capacitance at the base emitter junction. Okay, so this device, of course, or you take a transistor, of course, NPN, it simply means that you have a junction between the N and NAP, and then also another junction between the P and then the N. Okay, so that if I should take no. So if I should take, maybe I want to draw something like this, a simple one, of course. Okay, so I have okay, so this will be my N, okay. And then this will be my P, okay. And then this is another N. Okay, so this will be my base. All right, so the base terminal is here. This will be my collector, of course. Okay, and then I'll have my emitter here. Okay, all right. So this junction, okay, that is our base. Base. Emitter, and then you have your collector here. Okay, so this this is actually wasting my time anyway. Okay. So our VBE, okay, so that's to say base emitter voltage, okay. So there's a junction established between these two terminals. And because of that, you'll be having stored energy within the junction, okay. The same applies to the P and then the N, okay. So this junction, so I can call this one J1, junction 1. So maybe junction 1, and then so this junction. So this junction is junction 1, and then this is another junction. Okay, so junction 2. So that's you have your J2 here. Okay, good. So there will be store charges here in junction 1. There will be store charges in junction 2. Okay. All right. Now, if that is happening, then you need some time to be able to discharge the stored charge, okay, within that place, because you should be able to discharge it to allow for flow of electrons across the junction. So time is required. So that is the TD, which is the time required to what? Discharge the capacitance or the stored charge at the base emitter junction. Then the TRI is the time taken by the collector currents to rise from 10% to about 90% of the final value. So look at it here. So these are TD, okay. Let me go back to this. So this our T on, and then our TD is here, all right? So it starts from certain point to this value, okay, and that is the discharging time. But the thing is not actually in a full conducting state. Then TRI, okay, there is a rise in the collector current from a 10% point, okay, to 90%. So like we can see here, okay, if you take it from here, see here, okay, to about 90%. Then when it gets to this stage, from here going, the collector current is steady. It means that at this point, the device is fully turned on and is working. Okay, so there will be no need to further increase the base current or adjust your drive circuit for anything to happen again, because the device is actually turned on. It means that it has moved from the cutoff region to a saturation region. Okay, so that is what is happening as far as this time is concerned. Okay, now during TRI, your collector emitter voltage, okay, that's the VCE. Okay, so VCE will exist between, if you like, this place. I draw with this. There's this within this, okay, and then here. So you have your VCE here, okay, like that. So basically, this is going to fall, okay? So during this TRI, your VCE will fall from 90 to about 10%, okay, of its off-state value. So when you are looking at, yeah, I need a mouse, good. Yeah, so when you are looking at this, so for instance, the thing is conducting, okay? Maybe if you look at it from this perspective, or it's the same thing that we are trying to project from here, we projected it to this place, okay, the same concept. So from 90, it will fall, or it will reduce to a certain value, okay, like we have here, okay? So if it's going to reduce, it simply means that we are reducing the base current, okay? We are reducing the base current, but it will not entirely go off until the base current reaches certain value, okay? So that is what we are describing here. So the VCE falls from 90 to 10 of its off-state value, okay? So your TD depends on the magnitude of the base current, okay? Like I was saying, which can be reduced by a higher base current with high slope, okay? Hello, are you there?
Yeah, yes.
Yes, sir.
Okay, our time is almost getting finished. So let's see. But if we should pause here, okay, it would mean that you have to just continue from this point. I think you basically have just this slide and then the next one to finish this, and then we talk about power MOSFET. So you start reading on the MOSFET. You understand?
Yes, sir.
Okay. So the concept here, all right, is to just reduce the base current, and it will cause the collector current